Today, we're diving into something pretty wild from NVIDIA called DreamDojo. It's a whole new way to train robots, and it might just change everything. The idea is simple, but kind of genius. Forget painstakingly coding every single law of physics. Instead, what if a robot could learn complex physical skills just by binge-watching thousands of hours of human videos? Let's get into it. But first, think about this for a second. Pouring a glass of juice. You do it without even thinking, right? Well, for a robot, that simple action is an absolute nightmare. It's all about complex physics. You've got the changing weight of the carton, the splashy, unpredictable flow of the liquid, the exact angle of the pour. If the robot gets it wrong in the real world, it's a mess at best and a broken robot at worst. This one little task really shows you the huge mountain robotics has to climb. So, for years, the go-to answer for this has always been simulation. We build these virtual worlds, these digital sandboxes, where robots can practice over and over without breaking anything. But, and this is a big but, creating those virtual worlds has been a massive, massive bottleneck holding back progress.
Yeah, the old way was a slog. It meant someone had to sit down and manually code every physical rule. You needed perfect, expensive 3D models for every single object a robot might interact with. It was just incredibly slow and costly. But DreamDojo, it completely flips the script. It doesn't need a rule book for physics because it learns it all just by watching real videos. It literally watches pixels, and from that, it dreams up what should happen next.
And that brings us to the core concept here, the real paradigm shift. If you want a robot to understand how the physical world works, why not let it learn from the greatest collection of experts on the planet? Us. It uses our collective everyday experience as its ultimate textbook. The fuel for this learning engine is a beast of a dataset called DreamDojo HV. And this isn't just a bunch of random clips. It is a purpose-built, absolutely massive collection of first-person videos. Videos shot from the perspective of the person doing the action. And the scale of this thing, it's just staggering. First off, the sheer amount of video. We're talking about 44,711 hours. Let that sink in. That's more than 5 years of continuous, non-stop human activity for this AI to study. And it's not just a lot of the same thing. It covers over 6,000 unique, distinct tasks. Seriously, everything you can imagine, from folding laundry and packing boxes to cooking a meal and fixing things, all of it is in there, giving the AI this incredibly rich, broad understanding of how we interact with the world. And to top it all off, these tasks are happening in nearly 10,000 different scenes. Think about that. All kinds of different kitchens, different living rooms, different workshops with different lighting, different clutter. This variety is absolutely crucial. It's what allows the AI to learn general principles of physics that aren't tied to one specific place. Okay, so here's the big question, right? We have all this incredible human video, but a human hand is not a robot gripper. There are no motor commands or torque values in a YouTube video. So how in the world do you translate what a person is doing into something a robot can actually understand and execute? This is where the real magic happens. The answer is this really clever idea called continuous latent actions. The best way to think about it is like a universal translator, but for motion. The system watches a video, and instead of getting bogged down in the details of human hand, it extracts the pure essence of the motion, the pushing, the twisting, the lifting, and turns it into a universal language of action that any robot, regardless of its design, can understand. And here's basically how they do it. It's a 3-step process. First, the AI looks at 2 video frames, one right after the other. Then a really powerful model, a spatiotemporal transformer, analyzes the difference, the literal movement that happened between those 2 moments. Finally, and this is the key part, it distills all of that complex motion down into a super compact code made of just 32 numbers. That little bundle of numbers, that is the action. Now, to make sure the physics in the dream felt really, really right, the NVIDIA team made a few key refinements. For one, they taught the AI to think in terms of relative actions. Move the arm up a little bit instead of move the arm to this exact coordinate in space. It's way more flexible. They also figured out a smarter way to inject the action codes, and crucially, added a special check to make sure objects in the simulation stay stable and don't just glitch out over time. Okay, a simulator that can perfectly predict physics is amazing. But it's also kind of useless if it takes an hour to simulate 1 second of action. For this to be a practical tool that engineers and robots can actually use, it needs to be fast, like real-time fast.
So how did they crack that problem? They used a slick technique called distillation. Think of it this way. They took their huge, slow, but incredibly accurate teacher model and used it to train a much smaller, nimbler student model. The student learned to get the same results as the teacher, but in a fraction of the time. This trick slashed the number of calculations needed to predict the next frame from a hefty 35 steps down to just 4.
In the final result, over 10 frames per second. Now that might not sound like a blockbuster movie, but for a physics simulator in robotics, that is the magic number. It's fast enough for a human to control a virtual robot smoothly, and more importantly, it's fast enough for a robot to run thousands of what-if scenarios in its head to plan its next move. This makes the dream real. So we have this fast, accurate simulator that learned how the world works by watching us. What does that actually unlock? What can we do with it that we couldn't do before? Well, there are 3 huge applications here. First, policy evaluation. You can test a robot's programming, its policy, safely in this super realistic simulator before you ever let it loose in the real world. Second, and this is a big one, is model-based planning. The robot itself can use the simulator to look into the future, trying out thousands of possible moves to find the one most likely to work. And third, you can have humans directly control the virtual robot in real time to quickly create tons of new high-quality training data. And if you're skeptical, if you're wondering, yeah, but does the simulation actually match reality? Well, get this. When they compared the success rates of different tasks inside DreamDojo versus the success rates in the real world, the correlation was 0.995. That is astonishingly close to a perfect one-to-one match. It means what happens in the dream actually happens in reality. Let's look at a concrete example. They took a real robot and gave it a fruit packing task. The robot that used DreamDojo to plan its moves ahead of time, to think before acting, saw its success rate jump by 17% over the baseline. That is a massive real-world improvement, powered entirely by a better imagination. And taking a quick look at the data, you can see the trade-offs. They have a bigger 14 billion parameter model that's significantly better at getting the physics right. But it's the smaller 2 billion parameter model that, after that clever distillation process, hits that all-important real-time speed of over 10 frames per second. So if you take just one thing away from all of this, let it be this idea. DreamDojo isn't just a better simulator, it's a totally different way of thinking. We're moving away from painstakingly defining the laws of the universe, and we're moving towards creating models that can just learn those laws intuitively by watching. It dreams the results. Which leaves us with this final, fascinating question. For decades, just getting a robot to handle physical objects has been one of the hardest problems in all of AI. If robots can now start to master that simply by observing us, what's next? What truly human, subtle, and nuanced skill will we teach them now that they can watch and learn?